Hey guys, welcome back. So the next part that I want to talk about is the chemical equilibrium theories. We're going to talk about what's in the lab manual and what would have physically happened had we gone into the lab and done this experiment. And I'll talk a little bit about the data that's been presented to you so that you will know what you're looking at. And that is my plan for that part. So let me go ahead and move some documents around and then share so that you can see what I'm trying to talk about. So let me share my screen. So I'm currently looking at the chemical equilibrium section of the lab manual. This is experiment 1. This has been separated out for you and is presented in this folder, or it is available in the entire manual, which we could get to through course documents, lab manual. So it is there as well. What we see when we look through this lab manual is the name of the experiment and the objective, which will both need to be done when we do the paperwork. And I'll talk about that again when we talk about the paperwork. This will give you an introduction as to what this lab is trying to do. So this lab is meant to be able to study chemical equilibrium and to force some of the ways that we can look at things. So we're going to force this reaction to go all the way forward for one set of this, and then we're going to let it approach equilibrium for the other set, and then figure out what the equilibrium concentrations are and use that to calculate the equilibrium constant for this reaction. Okay. Now, we know that chemical equilibrium exists, and that is defined as when the rate of the forward reaction equals the rate of the reverse reaction. Now, I know we haven't talked about rate yet. I get that. But that's what this is talking about. And so from a high point view, we can't tell that anything's happening, but the reaction is going forward and backward, and we just don't see it. Over time, those concentrations do not change. So no net change is observed. That equilibrium constant, or a general equation, takes the form of K, so it's symbolized as K, is equal to the concentration of each reactant or each product raised to its stoichiometric coefficient over the concentration of each reactant raised to their stoichiometric coefficients. So my two products, C and D, have concentration C here, concentration D here. The stoichiometry of C is this little c, and that's the power on that concentration in the equilibrium expression. And then our two reactants, A and B, each to the A and the B stoichiometry in that reaction, also have powers of A and B in my K. Okay, so that's the form that always takes. It's always products over reactants. We always raise them to the stoichiometric coefficient of that reaction. Now, if I have done my stoichiometry differently, so if I were to do this, and let me share my piece of paper with you so that you can see what I'm talking about. So if we were talking about, and let me show, hold on, give me 2 minutes. I will get to where I want to be, I swear. So the actual equation for what we're going to be talking about is right here. So you'll see that. And this is on page 14 of this lab is where that equation exists. And so that says Fe3 plus SCN minus goes to FeSCN, and that whole thing is 2 plus. So that's a complex ion that's formed between that metal and that anion. Okay. Now, I have written that down, so this is just the same equation, and that's what we're looking at in terms of that equation. What was I doing? Oh, so I was going to say that the K we would write for this. Now, all of these are 1. Their stoichiometry is 1. There's 1 on each side. So our stoichiometry is always 1 in this one. But that would be the concentration of the FeSCN 2 plus, we must include the charges, over the concentration of the Fe3 plus and the concentration of the SCN minus. Okay, now that's the way this is balanced here. But if for whatever reason, instead of balancing it that way, I had done it as 2Fe3 plus 2SCN minus goes to 2FeSCN 2 plus, then the K for that would not be the same as what we wrote before. It would be FeSCN Fe2 plus squared over Fe3 plus squared times SCN minus squared. So that expression is based on the stoichiometry of the reaction as written. That becomes very important when we start moving into other things, because occasionally we'll have to balance it differently than we normally would. And you'll see things like this where we've multiplied the entire thing by 2. Okay, so that is important. All right, I'm going to erase all of this stuff that I did here so that way when we want this piece of paper, it will be clean. Because I'm going to be using this. Okay. So that's what we mean by it. It is based in the stoichiometry. Now, that expression is important. And of course, we're going to be measuring some things to be able to allow us to measure the concentrations at equilibrium for one part of this, and the concentration of each species as it exists when we make the calibration curve. So what we're trying to do is figure out what are the concentrations at equilibrium. If I start with this concentration of this thing and this concentration of this thing, what is that concentration at equilibrium for all of those species? And we can do that with the equation that we're looking at. So this right here, this FeSCN2 plus creates a really brilliantly red species. And so we can measure that because the amount of red that is produced by that particular species is a measure of the concentration of that species. So what we can do is look at how much light passes through that solution. So we take a spectrophotometer, it's a small box, it's like this. There's a hole in it where there's a light path that goes through that hole, and we pass light through that at a particular wavelength. Right here, we're using 447, and we look at, okay, what is the light that goes through that when it's just the little container that we put it in? It's called a cuvette. And then the background material, which here is HNO3, because all the solutions we're going to make contain HNO3. So if I take that as my background, then I can subtract that out from everything else. And if I do that, then the next solution that I make that has this colored complex will give me an amount of light that was transmitted through it. And it should be less than it was when there was no color in there. Okay, so our maximum value is 100%. We're going to go down from that based on the concentration. The higher the concentration, the lower the percent transmittance. Now, since we're measuring percent transmittance, i.e. how much light gets through, that's the inverse of the amount that was absorbed by the species. And it turns out that there is a law called the Beer-Lambert law that is a direct relationship between concentration and absorbance. In the spectrophotometry appendix, it talks about this relationship. So the Beer-Lambert law. And again, it's the absorbance is equal to the molar absorptivity constant times the path length times the concentration. Path length is always 1 centimeter, and your molar absorptivity constant is the slope of the calibration curve that you're going to make. And we'll talk about that in detail when we get to the data. Okay. So we're going to generate a calibration curve. The way that we do that, the way that we can know exactly what that concentration for that product is we set this reaction up such that there is a huge excess of one of these components. And we do that for the SCN minus. So we make that 3 to 4 orders of magnitude bigger than the iron. And that means every iron that exists in that thing is now going to be in the FeSCN side. Now they may come apart, but they'll immediately go back together with the next SCN that's next to it. Okay, so that's why we use such a big excess. In that case, we know exactly what the concentration of the FeSCN2 plus is based on the concentration of the Fe that I put in it. And so that means that we can generate a calibration curve because we'll know what the concentration of the iron is. We'll measure the percent transmittance put that into our Excel spreadsheet, which I'll get to when we get to that. And that will generate a calibration curve for us because it does the conversion between percent transmittance and absorbance. And then we get the absorbance versus concentration graph. We can find the slope, which is the molar absorptivity. And then when we have unknowns, we can measure that against the calibration curve to figure out what that concentration is based on the amount of light that came through. So that's the first part of the lab. So we have set this first part up such that we are making 5 different solutions, all with a huge excess of this KSEN. Notice not only do we have this KSEN at 5 mils, but it's 0.2 molar as opposed to 0.002 molar. Now our iron solution not only starts as 0.002 molar, but the other thing is that we take this 0.002 molar solution, take 10 milliliter sample of it, and dilute it to 25 milliliters. So it's now more dilute than it was when we started. And that's the solution we're going to use to make all of these knowns. Okay, so it's a big difference in concentration. So we will calculate what that concentration is, and we'll talk about how we do that in a few minutes. We'll calculate that concentration, and we'll fill in all the tables that we're going to put in our lab notebook with the volumes that we're using, the concentration, and the percent transmittance. Okay, that's the first part. That data can then be used to generate a calibration curve. But while we're in the laboratory, we want to set up the second part of this so that we can collect more data. Now, the second part of this, we don't use a huge excess of one of these two. We use relatively similar concentrations of both of these species, all right? So in this case, we're going to be using 0.002 molar Fe and 0.002 molar SCN, so same concentration. And then we're going to prepare our beakers with the Fe, the SCN, and some HNO3 according to this table, okay? Now, in the previous table, when we made our dilutions, all 5 dilutions had the same final volume. That was 25 milliliters. In this case, we're using 1 mil of the Fe in the first one, 1 mil of the SCN in the first one, and 4 milliliters of the HNO3 for a total volume of 6 mils. In the second beaker, we have 2 mils of Fe, 2 mils of the SCN, and then 3 mils of the HNO3. So 2 plus 2 is 4, plus 3 is 7. So 7 milliliters. So every volume is different. So we're going to need to keep that in mind when we do our calculations when we get to that. Okay. But this is how we would prepare those solutions. And then we would take and put those into the spectrophotometer, measure the percent transmittance. And then we'll take all of that data home to do all of the crunching of calculations. So what needs to happen in order for us to do this? Then we're going to have to talk about the lab notebook. So that's what we're going to do. That's how we're going to do it. This is all the theory behind how we do that. Okay. When we get to the calculations, you'll see that there are discussions about how we do those calculations. Right up here, we talk about using an ICE table to do these calculations, and we'll talk about that in detail when we do the calculations. But that talks about the theory of how we do that and why we do that. So we'll get to that when we get to that portion of it. So the ICE table is based in chemical equilibrium. It stands for initial change in equilibrium. Our initial concentrations, or whatever we put in the beaker, our change is based on the stoichiometry. So for every iron I put in, I need an SCN to go with it to make 1 iron thiocyanate. Okay. If this was 1 plus 2 SCN, then this X would be a 2X. Okay. And my equilibrium expression is going to be whatever I started with minus the change to give me that equilibrium. And that's what we put in to solve for K. Okay, so that's how we're going to do that. And that's how we do that when we don't know what those values are. All right. And we'll talk about the calculations when we do that. So I think that's everything I want to talk about for the theory section of this. This goes with the discussion that we had in the lecture about the chemical equilibrium theory. And I will talk about the lab part when we're in the lecture for the chemical equilibrium as well. They go back and forth a lot. So, but that's the theory part of this lab. So I'm, again, going to stop recording here. I'm going to stop sharing. I'll stop recording. And I will see you soon.